Hello dear students, I am Dr. Neelam Yadav from ABES Engineering College. I am preparing this lecture video on the topic nanomaterials. The content which I will be covering under this topic are preparation of nanomaterials, properties of nanomaterials, application of nanomaterials, and we'll be taking some of the examples of nanomaterials, that is CNT and spines. When we are talking about nanomaterials, there are some of the major terminologies which we must be aware of. Nanomaterials are generally the materials which are having dimensions and tolerance within the range of 1 nanometer to 100 nanometer. And when these nanomaterials are being used for the study of fundamental principles of molecules, that is called as nanoscience. And when we manipulate the material and its properties at the nanoscale for a particular target specific applications, then that method is called as nanotechnology. Now, nanomaterials are being classified on the basis of the number of dimensions they are having. The nanomaterials with three-dimensional structures are those which can be represented in all the three directions. And the example for these nanomaterials are some of the example for three-dimensional nanomaterial is, for example, we can take an example of graphite. This is a three-dimensional nanomaterial which can be used. Now, the second example for a two-dimensional nanomaterial is graphene. And an example for one-dimensional nanomaterial can be taken as nanotubes. Now, this is a three-dimensional nanomaterial with which we have taken an example, that is a graphite. For two-dimensional nanomaterials, the example we have taken is graphene, and this last picture which is being shown as of a carbon nanotube is a one-dimensional nanomaterial. Now, preparation of nanomaterials. Nanomaterials can be prepared by many methods. Some of the methods are being described over here. One is top to down and bottom to up approach. Another preparation method for nanomaterial is chemical vapor deposition. Another is chemical vapor condensation, gas phase condensation, pulsed laser deposition, and sol gel technique. These are some of the major methods in which nanomaterials can be prepared. Now here we are discussing about the top to down and bottom to up approach of manufacturing of nanomaterials. For top to down approach, generally a bigger size particle is taken. This bigger size particle on which this is called as bulk material. Patterns are generated and they're reduced to nanoscale. This is the nanoscale material or nanomaterial. When the size of the bulk is reduced, it is called as powder form. And when it reaches to the measurement of nano material or nanoscale, it is called as nanomaterial. This is top to down approach. They are bulk material and the pattern is drawn on this bulk material, and then it is reduced to powder size and then to the nanomaterial range. Top to down approach is generally used in electronic industries. Now, in bottom to up approach, here the beginning of the preparation starts with atoms or molecules. Let's take the size of atom or molecules, the smaller, very smaller size. This size, this is atoms or molecules. These are the starting materials which are being used for the preparation of nanomaterial by using the method of bottom to up approach. These nanomaterials, these atoms and molecules are brought to clusters. These are clusters, and they are increased in size to that of nanomaterial range. These nanomaterials are having a range of 1 nanometer to 100 nanometer. Bottom to up approach is generally used for the preparation of full rings. This is one of the most important method which is being used for the preparation of nanomaterials, top to down and bottom to up approach. The difference between these two, top to down and bottom to up approach, is we'll be discussing this difference. Top to down approach, and here we'll be discussing bottom to up approach. First difference is in the method in which it is being prepared. Like in top to down approach, we begin with a pattern generated on large scale. And then reduced larger scale, and then reduced to nanoscale. In bottom to up approach, here the method of preparation is we start from atoms or molecules and build up to nanomaterials or nanoscale. Now, the second difference between the top to down and bottom to up approach is top to down approach is quite expensive. Bottom to up approach is less expensive. Top to down approach is generally, this approach is slow. And is not suitable for large scale production. while bottom to up approach it is suitable for large scale production. Some of the example of top to down approach, it can be done by erosion method. It can also use a method of mechanical grinding. While for bottom to up approach, the examples are molecular self-assembly, gas phase agglomeration. These are the differences between the top to bottom, top to down and bottom to up approach. Now next we'll be discussing about the properties of nanomaterials. Here the nanomaterials are having very unique property, and this unique property is due to the change in the particle size from classical physics to quantum physics, and the size is reduced from less than equal to 100 nanometers. The various properties which are being affected by the particle size is the size effect, specific surface effect, and composition effect. When we are talking about the size effect, the major properties which are being changed are melting point. The major properties which are being changed are melting points, solubility, transparency, and the catalytic behavior of the material. When we are talking about the surface area effect of the nanomaterials, this directly affects the properties like dispersibility, conductivity, and catalytic behavior also. In addition, it also affects the optical properties of the material. The nanomaterials are also showing the effect due to the composition, and this cause different physical and chemical behavior of the material when the composition of the particles is varied. The various applications of nanomaterials are in different industries. Like we are having the application of nanomaterial in chemical industries in the form of fillers, for point systems, for coatings. These are some of the examples for chemical industries application. In automobile industries, they are used in lightweight constructions, painting, also in some of the sensor parts. In medical industry, medicine industry, it is used for drug and gene delivery, detection of proteins, also in tumor detection. In case of electronic industry, it is being used for Data memory, glass fibers, as in glass fibers. For energy sources, they are used in fuel cell, solar cells, batteries. For cosmetics, they are used in sun protection creams. Toothpaste, etc. So these are some of the major applications of nanomaterials in various industries. These are some types of nanomaterials, like polymers are also in the form of nanomaterials, dendrimers, liposomes, gold nanoparticles. Now we are taking some of the examples of nanomaterials, and this is an example of carbon nanotube. Generally, carbon nanotubes are sheets of graphite being rolled up to make tubes. And these tubes are having the diameter of 1 nanometer to 100 nanometer. They ranges from 1 nanometer to 100 nanometer. Carbon nanotubes can be single walled or they can be multi walled. This is an example of single walled carbon nanotube, and this is an example of multi walled carbon nanotube. Now, preparation of single walled and multi walled nanotube. When we are talking about preparation of single walled nanotube, it is prepared up from graphene sheets. Generally, graphene sheets are single layer of graphite. This is a graphene sheet. When these graphene sheets are rolled up, they form single walled nanotube. Generally, single walled carbon nanotube has a diameter range of 1 to 2 nanometer. Now, this is a graphene sheet, and when graphene sheet is rolled up, it forms single walled nanotube. When this graphene sheet is layered up to form multi-layered structure, it forms graphite. This is one layer of graphite. Now, attached to this by weak van der Waals force of attraction is another layer of graphite. When graphene sheets are layered up, they form graphite. When this graphite is rolled up, then it forms multi-layered, multi-walled carbon nanotube. This is multi-walled carbon nanotube. And the diameter range for this is 7 to 100 nanometer. This is multi-walled carbon nanotube. Single-walled and multi-walled carbon nanotube are related as multi-layered single-walled nanotube forms multi-walled carbon nanotube. Now, the major properties of carbon nanotube are they are having exceptionally high tensile strength. They are having exceptionally high tensile strength. Carbon nanotubes can be used as an insulating material, semiconducting material, or conducting material, and that depends upon the way the graphite structure spirals around the tube. Carbon nanotubes also possess large surface area. Carbon nanotubes show good properties in electron emission. They are reported to be thermally stable in vacuum up to a temperature of 2800 degrees centigrade. Carbon nanotubes exhibit excellent electrical and mechanical properties. These are some of the major properties of carbon nanotube. Some of the major applications of carbon nanotube are they are used as needles in cancer therapy. They are used as an excellent electrical conductivity, heat transmission capacity. They have heat stability, low density, and high strength, and can be used as fillers in composite materials. The various applications for composite materials are like polymer LED, ultra-resistant material are used as reinforcement fibers, electrical energy storage applications. Now, another example of nanomaterial, which we'll be considering over here, is a super paramagnetic iron oxide nanoparticles. This is also called as spions. These spions are generally synthetic gamma ferric oxide, which is also called as megamite. Another example of spions are magnetites and hematites. These particles are also ranging in a they are having a diameter range of 10 nanometer to 100 nanometer. Spions are generally made up of iron oxide core. They are generally made up of an iron oxide core. Like we can see it in this figure. This is made up of an iron oxide core and it is surrounded by hydrophilic. Hydrophilic means they are attracted towards the solvent or water. Hydrophilic polymer coating. So, in case of spions, the core position is made up of iron oxide, and the iron oxide is surrounded by hydrophilic polymeric material. These hydrophilic polymeric material can also be fabricated from dextran, starch, alginate, PLGA, that is polylactic co-glycolic acid, and polyethylene glycols. The applications of spions are generally used in the contrast agents as a contrast agents for MR imaging. They are used as iron replacement therapies. They are used in drug deliveries. They are also used in cell and tissue targeting. These are some of the references which I have considered while preparing this lecture video. Thank you.